The Australian summer. It's 45 degrees Celsius outside. That is 113 degrees Fahrenheit. It's scorchingly hot. In rural Victoria, a branch falls over a power line. This little spark starts a bushfire that ravages the countryside. This is the focus of my talk today. We're looking at bushfires, or fires that start when vegetation come into contact with power lines. I'm Sevvandi Kandanaarachchi, and this is joint work with Mario Andres Munoz Acosta and Nandini Ananthirama. After the devastating Black Saturday bushfires in 2009, the Victorian government initiated the Power Line Bushfire Safety Program, and they did research on how fires can start from power lines. As a part of this program, they did a lot of experiments which were inside a container. In the container, they set up this rig as, like seen in this picture, and there were power lines running. And they put branches on these power lines, and they go out of the container and then switch the power on. Then they recorded the current and the voltage from this experiment. Both the low frequency and the high frequency currents, denoted by LF and HF, and voltage were recorded. So, and this data was made available to the public, and we asked the question, so if a branch falls on a power line, or if a power line breaks and comes into contact with a tree, like it snaps and then comes into contact with the tree, can we predict if it ignites or not from the current patterns and the voltage patterns that you get? That was the question that we asked, and we did it using the experimental data. So there was raw data that was collected as a result of this experiment, and we pre-processed it. So this figure shows the pre-processed data. So what we did was we computed the RMS value, so that is the root mean square value of currents and voltages. So this is a current, the low frequency current, and this is the blue line gives the RMS value. And here, what we have is, this was generally divided into phases, phase 1, phase 2, phase 3, and so on. And what the people at the Victorian government who were doing the Power Line Bushfire Safety Program, that they told us that the fires happen in phase 2 and onwards, not in phase 1. And phase 2 is said to start at the peak of this current. So this is the first maximum. After that, it's phase 2, and then of course they have phase 3 and on. But this is where the ignition, the fire happens. In phase 1, it's not. The fire doesn't happen as yet. So the question that we looked at was using phase 1 data, actually using half of the phase 1 data. So we're looking at that point there, like somewhere between, so if this is 20 and it starts around 5-ish, so somewhere between there, we start the data from here to here, and then can we say if it ignites or not, using half of the phase 1 data. So that was the question that we asked. And to do this, so we had the raw data, the currents and the voltages, the low frequencies and the high frequency currents. So we pre-processed it and we computed features. We computed 240 features in total. So there were frequency domain features that were used, that we computed, and also there were time series features, the traditional time series features that we computed. And we used it using a rolling window. And so, using a rolling window, we got these features and used it to classify whether they were igniting or not. So, to compute the time series features, we used the R package TS features, and in total we had 112 features. So, they had things like spikiness, how spiky is the data, how linear is the data, the curvature of the data, and then autocorrelations, and second derivatives, like these kinds of features we had. And then there were frequency domain features. The frequency domain features were computed using the fast Fourier transform, and after you compute the fast Fourier transform, you get frequency bands. So we divided the frequency spectrum into 4 frequency bands, and then for each frequency band we computed summary statistics of the amplitude of that particular band. So from the frequency domain we had 128 features. And then we fed these features to a random forest model, and we used tenfold cross-validation. Again, we only used half of the phase 1 data because one of the goals was to predict it before it happens. So there should be some time for us to predict it. So this was the mean cross-validation accuracy, where we got about, if we used all the tests, they had about 1,000 tests, and some of them were not for the valid test came around to 750, I think. Some of them were classified as not valid. So of those tests, we got 83% accuracy if we used all the tests. But then some of the tests had very short phase one time periods. So some of them had like 2 seconds of phase 1 and 3 seconds of phase 1. So that would mean if you only had 2 seconds of phase 1 time, then we have to predict it using just 1.5 seconds. So, and that's kind of challenging. So then we looked at, okay, if we remove the test with very short phase 1 time period, so that is, if we look at the test with phase 1 time greater than 4 seconds, then the accuracy improved to 86%. And then if we again looked at a phase 1 test greater than 8 seconds, it improved to 87%. So there was a slight increase if you look at tests which were not very small time periods, like not very small phase 1 time periods. Right. So so those were the classification results that we got from the random forest model about predicting if it ignites or not. And then after doing that, we also so we had these 240 features. So computing 240 features, if you're going to implement this in real time, it might be challenging. So we wanted to kind of get the idea of what were the most important features. So we clustered these features in this high-dimensional space, and for each cluster we picked a feature from that cluster. We used a silhouette analysis to pick the number of clusters and find. So the purpose of this was, by clustering features, you know what the similar features are, and then you find you get a feature of that representative cluster and then do the classification process again. So we managed to reduce the features to 36 features from 240, and still we got an accuracy of about 82% using tenfold cross-validation and the same a random forest model. And then we looked at, okay, of these 36 features, what were the features that were most relevant for prediction? And we found that the features that were most relevant was how fast the current changed. The way the current changed if it's going to ignite was different to the way the current would change if it did not ignite. So the linearity of the current, the spikiness, and the curvature of the current. So those were all the way the current changes. Those were the telling features, regardless of. Even if we looked at the full model of 240 features, these features were the most kind of important. And even if we got the 36 features, these features came to be very important. And also there was this frequency domain feature, which is the maximum amplitude of the low frequency band of the current. So we got some understanding about the telltale features that the current changes in a kind of different way if there's something going on and if it's going to ignite. So in summary, the project was about predicting ignition before it happens when a branch falls on a power line. And so the free version is available at this website, and this paper was accepted at IEEE trial sections on power delivery, and we'd like to thank ASEMS for research support funding, and thank you all for listening.